Hi, everybody. Thank you for coming to listen to me speak today. My name is Jay Ashworth, and I'm a student from the University of Tennessee, currently studying under Dr. Michaela Talfer of the Global Computing Lab. I recently completed my master's degree, also at the University of Tennessee in the spring, and I'm going to be continuing on to working on my doctorate's degree in the fall. Today, I want to talk to you a little bit about a tool that we've been developing in collaboration with Lawrence Livermore National Lab called the Flux Emulator. And so, without further ado, first I want to talk to you a little bit about El Capitan. So, as many of you probably know, El Capitan is currently considered the most powerful supercomputer in the world in terms of Linpack score, reaching 1.742 exaflops on the top 500 list as of November 2024. And with systems like El Capitan, and other exascale systems that are to come in the future, they propose a significant resource management challenge, not only because of the sheer scale of the resources that they have. In the case of El Capitan, a little over 11,000 compute nodes, um, but also with these new advanced systems that are coming out, they propose new resource paradigms, such as on El Capitan, there are rabbit nodes that are dynamic and can switch between being local storage or shared job global storage. And so, with advancements like these coming online, a tool in the case of El Capitan that's been introduced to address the issue is known as Flux. And so, what Flux is a resource and job management system, or RJMS, that is designed to provide hierarchical and flexible scheduling for modern exascale systems. And it does this through a combination of its hierarchy of brokers architecture, which is depicted in the figure on the left here, um, but also through its extensive modularity through its broker modules and other plugin systems. Um, and what specifically a broker module is one of the services within Flux that actually make it useful. So pretty much all of the services that users and administrators will work with on an HPC system are broker modules. Some examples of broker modules within Flux are the job manager, the resource module, the job exec module, and the scheduler, which in the case of Flux is called Fluxion. Um, and we want to highlight Fluxion because, well, it's one of the primary focuses of our research. It is an open area of research in terms of making it better. And what Fluxion provides is a graph-based resource representation um, that allows for more effective scheduling of accelerators and dynamic resources like the rabbit nodes on LCAP, um, as well as allowing you to take advantage of net topologies in your network. Like if you wanted to make a scheduling policy that accounts for um, how close together nodes are in a system. And so, with new schedulers like Fluxion being introduced, that introduce new resource models, as well as new resource paradigms like the rabbit nodes on El Capitan, there's a large need for tools that can accelerate research into schedulers and scheduling policy without impacting production systems. And that's what we provide with the Flux Emulator. So what we're able to do is essentially test scheduling policies through the use of historical job data without actually using a production system and saving a lot of all of the time that would be required to actually get results on a production system. And we do this through as a result of the unique modularity of Flux and this can be explained through the job lifecycle in Flux. So what I'm going to do now is take you through the 6 steps of the job lifecycle in Flux, and then explain how we make modifications to this process in the Flux emulator to allow the features that I described. So whenever Flux is initialized or the Flux instance is started, what happens is all of the configurations loaded in, Flux prepares itself for user job submission, and important processes like setting up the resource graph in Fluxion and then the resource module occur. And so after all of that's said and done, users are able to submit jobs like normal to the system in the second step. And from the user perspective, not a lot really happens until the results given back to them. But in the case of Flux, there's a few other steps that happen in the middle. Um, so the next step after a user submits their job is the validation of the job. So actually, the job manager in this case will verify to make sure that the user's job request is sane, essentially. So for example, if they request way more nodes than the system has available, then in this step, the Flux will tell the user that their job isn't going to be able to run. Um, then after that's done, the scheduler will take over and it will attempt to find a slot within the resource graph or resource list that can fit the user's resource request for their job. Whenever it's done this, the scheduler will um, allow the exec system to take over, and the job will actually be launched on the nodes that were scheduled. Then, of course, whenever the job is finished, the result will be given back to the user by Flux, and the resources get released back to the system. Now, with those steps set in place, there's a few modifications that we make with the Flux emulator to be able to allow us to skip the time required to analyze scheduling policies and also make Flux think that it's using a large production system while it's only running on something like a desktop computer. So the first step in this process that's required is in the initialization step. So I mentioned in normal Flux, a configuration is loaded in, taken from the system to allow Flux to understand the system that it's running on, and the resource graph and everything's created. Well, in the emulator, what we actually do is just provide a fake resource model to Flux, and through careful orchestration of the module, specifically the resource module and the scheduler, we're able to make this happen without Flux taking notice that the resources aren't in existence. The next major modification that we make is in the job exec module. As you can see, comparing these two pictures side by side, the most obvious change is that job exec has been replaced by the sim exec block. And so what SimExec is kind of like a dummy exec module that we introduced that pretends to Flux. It pretends that it is the exec module in the eyes of Flux. It sends all the appropriate communications that the exec module would, um, but in actuality, it's not running any jobs. And this allows us to run all of the other components of Flux normally as if they were on a real system. And then finally, the last piece that we've added is in the form of this job sync additions block over here on the job manager that allows us to keep track of the internal state of the job manager, and it allows us to understand what the status of the job is within Flux. So now that we have our emulator, and now that maybe you have an understanding of how it works inside of Flux, we want to demonstrate a use case of the emulator and show you how it works in practice. So to do this, the first thing we had to do was generate a set of jobs that we can use to run on the emulator. And this is depicted by the plot here on the top left. Um, we generated 100 equally long, but varying resource requirement jobs between 1 and 100 nodes. And what this allowed us to do was compare something like first come, first serve scheduling versus backfilling scheduling, and have some room for improvement when we introduce backfilling. And so what we did is we input this set of jobs into the Flux emulator and had it run through all of the jobs as if it was on a real system and see how the scheduler decided to schedule jobs. And that's what these plots are illustrating. So as you can see in the top graph or the top plot, this is the result for the first come, first serve scheduling. As you can see, there's a lot of white space there at the top where the next job in line just simply couldn't fit in to be scheduled. And so the system wasn't utilized to its full extent. But on the bottom, we introduced conservative backfilling. And as you can see, and as is probably expected, we get a lot more system utilization, moving from 77 to about 93% utilization. And we cut down on the make span by a significant amount. Um, but the most important part about this is that it was run on our tool, the Flux Emulator, and in a matter of about 20 seconds, we got results that would have taken over 7 hours to collect on a real system. Now, we also performed this overhead measurement test, and the idea behind this is that maybe we would want to use the Flux emulator to produce a performance study of Flux. Maybe if we introduce a new scheduling policy, we want to see how long, what the overhead is for actually performing scheduling with our new policy. And so it's important that the emulator doesn't introduce significant overhead into Fluxion specifically, but the rest of Flux as well, as a result of its code. And so what this test is represents is we submitted um, sets of 1,000 and 10,000 small jobs to Fluxion and measured the throughput in which for these jobs to return. Um, what we observed is that across Fluxion and then Fluxion with the emulator code, there wasn't a noticeable difference in the amount of time or a noticeable difference in the throughput, which was a very good sign for us. Now, with that said, what we learned today is that, um, as I just mentioned, the emulator doesn't introduce overheads into Fluxion, and we're able to perform studies of scheduling policies. And in the specific experiment that we ran, we were able to realize a reduction in make span by 16.7%, an increase in system utilization from 77.5 to 92.9% by deploying conservative backfilling over first come, first serve. And overall, our Flux emulator shows promise as a tool to advance scheduling policy for Fluxion. Now, the next steps for the emulator are to, of course, compare the performance of the emulator to a live cluster environment and to perform scaling tests to understand the limits of the emulator. But more interestingly, some things that are in the pipeline are to use it to study more interesting scheduling policies, such as topology-aware scheduling or power-aware scheduling, and possibly even multi-cluster scheduling. Um, but yeah, um, that's all I have to talk about today. And once again, I just want to thank you for listening to me. And yeah.